Let's now take a look at an example. So in this example, we have a current carrying filament as shown below in the figure, and we want to find the magnetic field intensity H at some point -3, 4, 0. So we can see this current carrying filament has 3 amps. It's starting at the point 0, 0, infinity, and it's coming down towards the origin. Once it reaches the origin, it's turning and it's going along our x-axis to the point infinity, 0, 0. So we have something that looks like this. And of course, our point of interest P is also labeled back here as well. So one thing to note is that this is an example from the textbook. So this is example 7.2. However, I've updated the angles and how they're defined to match the previous videos and the initial definition given in the textbook. Just sort of a warning in case you're trying to compare to the textbook and things look a little bit different. Okay, so the basic idea here is that we want to use superposition the same way that we did when we were talking about multiple charge configurations. So we want to use our superposition principle, and we can then say that our overall magnetic field intensity at our point P is going to be equal to H1 plus H2, where our H1 is going to be due to the segment on the z-axis, and our H2 is going to be due to the segment on the x-axis. So segment on z-axis, and this is going to be our segment on the x-axis. And so we're basically just breaking up the problem and we're looking at one piece at a time. So there's our z-axis, there's our x-axis. So as always, I would encourage you all to maybe pause the video right now and try to set this up or work through it yourself before coming back to the video to see the solution. So what we're going to want to do is define our angles the same way we had done in the previous video. So let's start by looking at our H1 segment. So we're going to be considering the portion of the filament along the z-axis. And so if we're doing that, what we can do is we can define our angles alpha 1 and alpha 2. So remember, we're going to draw some line up to the endpoint. And so let me just draw it here as sort of a placeholder, but of course we know that's going to be going up that direction. And remember how we defined our angles. So alpha 1 corresponded to the angle that was towards the start. So up here, that's going to be in this direction, just because our current is coming downward, whereas before it was coming upward. And so remember, our angle also sort of went the opposite direction of the current. So it's going to be on this upper side of the line as opposed to the lower side, because our current, again, is going from top to bottom now. So this is going to be our alpha 1. And again, what we can consider is as this is going towards infinity, that alpha 1 is ultimately going to be going towards an angle of 180 degrees, excuse me. Our second angle, alpha 2, can be realized by drawing our position vector from point P to the other end of the line, and in this case we have some finite point. And again, we're going to draw this angle as going sort of down towards where the current is coming from, so this is going to be our alpha 2. And what we can see in this case is that alpha 2 is going to be 90 degrees. So let's come down here and we can say we're considering our z-axis segment. And we're going to use our general equation from the previous page, and we said that our alpha 1 is equal to 180 degrees and our alpha 2 is equal to 90 degrees. And so what we notice is that we could actually use the special equation for our semi-infinite line in this case. And that's only true because this point P is quote-unquote lined up with one of our two endpoints for our semi-infinite line. But let's go ahead and plug it into our more general equation just to see that we get the same thing. So using that in our general equation, our angles up there, we have that our H1 is equal to our current, which is 3, divided by 4 pi rho. And now we have cosine of alpha 2, which is 90 degrees, minus cosine of alpha 1, which is 180 degrees. And so of course cosine of 90 is going to go to 0, cosine of 180 is -1, so we get 0 minus a -1, which is of course just going to be 1. And as we expect, we get current divided by 4 pi rho in the phi direction, which is the same as we would have gotten if we just used our semi-infinite line equation directly. Okay, so now we have sort of two pieces of information we need to fill in. We need to figure out what our rho is, and so remember our rho is the perpendicular distance, and our phi, which we defined as our u of L cross with our u of rho. So again, very important to keep in mind that these two things, our rho and phi, are locally defined. So in order to figure those out, what we're going to do is we're kind of going to look at this triangle, which is in our xy plane. So we have some triangle here, which is in our xy plane. So let's take a closer look at that. Okay, so let's come down here and say we've got our -3 in the x, we've got our 4 in the y, and so this is going to be the distance from our origin, which is where our endpoint is, to our point of interest P. So this is our origin, so this is 0, and we have, this is a right triangle, so we're going -3, so a magnitude of 3 in x, and we're going over 4 in y, and so our perpendicular distance is going to be rho. Okay, so from this triangle, of course, we can see that our rho is just going to be equal to the square root of 3 squared plus 4 squared, which is equal to 5. So there's one of the two things solved. So we know what that rho value is right here. So now we just need to figure out the u of phi. So remember, in general, we had that our u of phi is defined as u of L cross with u of rho. Okay, so we can figure out u of rho by sort of knowing that we have this negative x direction. So really we have this negative x direction and this positive y direction. So if we want a unit vector here, we can say it's the rho vector divided by the magnitude of rho. So that's going to be -3 divided by 5 in our x direction plus 4 divided by 5 in our y direction. So there is our unit vector in our rho direction for this particular case. Again, noting that this doesn't line up with our normal definition of rho for our cylindrical coordinates. This is locally defined. So now for our u of L, so remember that's the direction that our current is flowing. And in this case, because our current is flowing downward, that's going to be in the -z direction. So our u of L is going to be equal to -z. So we have u of phi is equal to negative u of z, and then we're crossing that with this expression here. So let me just copy this and save a little bit of time, just paste that, and so we're doing this cross product. So now remember, our cross product properties said that if we have A cross B plus C, then that's just going to be A cross B plus A cross C. So we sort of break those two up. So let's start by looking at our A cross B. So if you don't want to go through this formally and sort of have this, set up the 3x3 determinants and all of that stuff, because we just have these unit vectors in x, y, and z directions, what we can do is think about our right-hand rule. So if we have -z cross with -x, we put our fingers on our right hand in the direction of -z, we curl them towards -x, and we see that our thumb is pointing in the direction of y. So we know that our u of phi is then going to have a direction in u of y for that first term, and we have a magnitude of 1 and a magnitude of 3/5, so we have a magnitude of 3/5 then. Now for the second term, it's going to be A cross C, so now we have -z cross y. So we're going to put, again, the fingers of our right hand in the direction of -z. We're going to curl them towards y, and we see that our thumb is in the direction of u of x. Then we have the two magnitudes, which is 1 and 4/5, so we're going to have 4/5 in the x direction. So this is going to be our u of phi that we plug in. So from here, it's just a matter of plugging that in, and then of course we have the 3 divided by 4 pi. So if we evaluate all of that, we can get an overall expression for H1, which is equal to approximately 38.20 in our x direction plus 28.65 in our y direction, and that is milliamps per meter. And so again, one thing to note here is that I've sort of switched this around, so my u of y is now my second term and my u of x is now my first term. And one other thing to note too, again, is that we could have just used that semi-infinite line equation to go directly to this point, but we still would have had to do all of this sort of trigonometry to figure out our rho and our u of phi. Okay, so we're halfway through the problem. So we found that H1 component, and now we're interested in the H2 due to this segment along the x-axis. All right, so let's come down here and let's say we want to find now our H2 component. Once we have that, we can just add H1 and H2 to get our overall distance. So let me go ahead and erase our lines that we used for our alpha 1 and alpha 2 in the case of the z component, and let's look at it now for our x-axis. So the same thing we can do, we can draw these lines to our points. So I can say, let's draw a line to our starting point like this. And again, remember the angle is going to be defined as sort of where the current is coming from. So it would be on this side to the negative x-axis. So this is going to be our alpha 1. And similar thing to our endpoint, which I'm just going to pick an arbitrary point here, but remember this is sort of going towards infinity, and this is going to be our alpha 2. So let me actually write that outside. So this is our alpha 2. And so what we can see is as that is going towards infinity, so remember we sort of have this point going towards infinity, what we can see is that alpha 2 is ultimately going to be going towards 0. It's going to become 0 as we go towards infinity there. One important thing to note is that for this segment on the x-axis, we cannot use our semi-infinite line equation. The reason is that our p is not lined up with the starting point of our semi-infinite line. So because of that, we do have to use our more general expression and find our alpha 1 and our alpha 2 and then plug them into that. So let's go ahead and go through that process. And as we're finding that alpha 1, we're going to consider that same triangle that we did before where we had -3 in x. So we had -3 in x, 4 in y, and we had some distance there. Let's see, it was trying to, so we have something like that. So let's go ahead and take another look at that triangle. We'll figure out our alpha 1. We said this alpha 2 is ultimately going to be 0. Okay, so coming down here, same triangle, 3, 4, and we know that that is going to be some distance that's equal to 5. And what we're interested in now is this angle alpha 1. So of course, cosine is adjacent over hypotenuse, so we can say cosine of alpha 1 is equal to 3/5. And because ultimately in the equation, we are plugging in cosine of alpha 1, we don't even necessarily need to solve for that angle directly. And we also, of course, again, let me just write that we had alpha 2 is equal to 0. So if we have cosine of alpha 2, that of course is going to be equal to 1. Okay, so we're almost ready to plug into that general expression. The two other things we're going to need again are our rho and our u of phi. Again, both of those are locally defined items. So our rho, remember, is the perpendicular distance from the line where our filament is, so the axis of our filament. So that's basically just the perpendicular distance from P to our x-axis here. And of course, that's just going to be our y position. So our rho in this case is just going to be 4. So we have rho is just equal to 4. Okay, and then one last thing we need to figure out is that u of phi. And so let's go back to our general expression. We know that our u of phi is equal to u of L cross u of rho. So now we see our current is coming out along our x-axis. So our dl is going to be in the positive x direction. So this is going to be u of x. And as we just described, our rho is coming out from the x-axis towards our point. So because of that, our u rho is going to be the same as u y. So again, we can use our right hand rule. We know that if we put our fingers on the right hand in line with x, we curl them towards y, and we see the result where our thumb is pointing is going to be in the z direction. Okay, so now we have all of these components ready to plug into our expression. So we go back to that expression for our finite straight segment that carries current, and we can say that our H2 is going to be equal to 3 over 4 pi. Now we found that our rho was 4, so we plug that in for rho. And now we have cosine of alpha 2, which is 1, minus cosine of alpha 1, which is 3/5. And our u of phi direction is going to be u of z. Plugging all of that in, we get approximately 23.87. in our U of Z direction. And again, that's going to be in milliamps per meter. So the last step is to just combine our H1 and our H2. In this case, we see H1 and H2 are purely X and Y, and H2 is purely Z. So we're just going to get a total H, which is each of those components just sort of added together. So from our H1, we have the 38.20 in our X direction. We also from H1 have 28.65 in our Y direction. And then from H2, we have 23.87 in our Z direction. And all of those were in milliamps per meter. And in the textbook, you can also see that this is converted to polar coordinates, cylindrical coordinates. So of course we could put this in terms of our unit vector of rho, our unit vector of phi, and our unit vector of z. And in that case, we are going back to our more general definitions. We're no longer using our local definitions. We can also consider does this make sense as an initial sanity check? We can come back up to our diagram here and we can use our right hand rule. So for instance, if we're looking at our X segment, we put our thumb from our right hand in the direction of our current, and we see our fingers are curling around in the direction such that at P, our field is purely going to be in the X direction. Conversely, if we're looking at the segment along Z, we put our thumb in the direction of the current, and now we're curling our fingers on our right hand, and we see it sort of coming around in this direction. So that means at point P, it's not purely in X or purely in Y, but we're going to have some combination. And so that's what we saw with our X and our Y component. Both of those were positive as we are seeing with this sort of double check of our work here.